The floor you stand on tonight is not solid ground. It is the frozen surface of a 4 billion-year-old river of fire. And tonight, the Earth is finally ready to whisper the secrets it has spent eons trying to tell. The redwood does not count its years the way you do. It does not mark birthdays or seasons with celebration. It simply stands, and in standing, it becomes a monument to patience itself. Some of the tallest coast redwoods alive today were already ancient when the Roman Empire fell. Their roots were drinking from California's fog-drenched soil, while human civilizations rose and crumbled like sand castles at high tide. These trees can live for more than 2,000 years, their trunks swelling to diameters that would dwarf your living room, their crowns piercing the sky at heights exceeding 300 feet. The forest floor beneath a redwood is a different world. The air tastes of moisture and decay, sweet and earthy, like bread left too long in a cellar. Moss cushions every surface, soft as lamb's wool, and the bark itself, thick as a mattress, fibrous and red-brown, crumbles slightly under your fingertips, releasing a scent somewhere between cinnamon and wet stone. When wind moves through the canopy, it does not roar, it whispers, it hums. The sound is so low and constant that it becomes a kind of silence, a baseline frequency against which all other sounds are measured. What does it mean to live for 2 millennia? To watch the same patch of earth for longer than any empire, any language, any religion? The redwood does not philosophize, but its existence poses the question anyway. It suggests that time is not a river, but a spiral, that patience is not passive, but generative, that to stand still is to participate in the deepest form of change. The tree does not resist time, it collaborates with it. The light filters down in shafts. Dust motes hang suspended, golden and slow. Nothing moves quickly here. Even the air seems to hesitate before shifting. The redwood stands. The centuries pass. The forest breathes. Beneath the soil of an old-growth forest, there exists a communication network so vast and intricate that scientists have taken to calling it the Wood Wide Web. Fungal threads called mycorrhizae connect the roots of trees, allowing them to share nutrients, water, and even chemical warning signals. A mother tree, often the largest and oldest in the forest, can recognize its own offspring and send them extra carbon through these fungal highways, giving young saplings a better chance of survival in the shaded understory. This is not metaphor. This is measurable, documented biology. Trees take care of their young. The fungal threads are finer than human hair, white and ghostly when you unearth them, and they smell faintly of mushrooms and damp paper. They stretch for miles, weaving through soil that is less dirt and more living tissue. A matrix of roots, decomposing leaves, beetle larvae, and bacterial colonies so dense that a single handful contains more microorganisms than there are humans on Earth. When you kneel and press your palm to the forest floor, you are touching a mind, not a brain, but something older and slower and more distributed. If trees can nurture their children, if they can warn each other of danger, if they can share resources across species boundaries, then what is a forest? Not a collection of individuals, but a single organism, ancient and patient and impossibly complex. The forest does not think in words, but it thinks. It remembers. It adapts. And it has been doing so since long before we arrived to name it. The forest is never silent, but it is never loud. Water drips from leaf to leaf. A branch creaks. Somewhere, a beetle chews through bark. The fungal threads pulse with sugar and signals. The mother tree stands, her roots entwined with her daughters, her sons, her neighbors. Time moves differently here. A single oak tree can support more than 2,000 species of insects, birds, mammals, fungi, and plants. Its acorns feed squirrels, deer, and jays. Its bark hosts lichens and beetles. Its leaves become mulch, which feeds the soil, which feeds the tree, which feeds the forest. The oak does not give grudgingly. It gives because giving is what it does, because its survival is inseparable from the survival of the creatures that depend on it. Ecologists call this a keystone species, but the term feels too clinical for what is happening here. The oak is not a species, it is a world. The bark of an old oak is deeply furrowed, rough as a crocodile's back, and it smells faintly of tannins, astringent, almost medicinal. If you press your nose close, you can catch the scent of the insects living in the crevices, a faint musk, like old paper and pepper. The leaves, when crushed, release a green, bitter smell, sharp and clean. In autumn, the acorns fall with soft thuds, and the air fills with the scent of their split hulls, nutty, sweet, faintly reminiscent of coffee. To be a keystone is to hold the arch in place. Remove the oak, and the arch collapses. 2,000 species lose their anchor. The forest does not end, but it changes, and the change ripples outward in ways we cannot fully predict. The oak teaches us that nothing exists in isolation, that every life is a thread in a web so vast and tangled that pulling one strand might unravel something 100 miles away. The oak stands, the acorns fall, the squirrels bury them and forget where. New oaks rise. The forest continues patient and unhurried as it has for millions of years. The Amazon rainforest produces roughly 20% of the Earth's oxygen, but it also consumes nearly all of it through respiration and decomposition. The net contribution to atmospheric oxygen is close to zero, and yet, the Amazon is often called the lungs of the Earth. This is not entirely wrong, but it misses the deeper truth. The Amazon does not breathe for us. It breathes for itself. It is a closed system, a world unto itself, recycling its own air and water in a cycle so efficient that rain falling in the western Amazon may be transpired and rained out again 5 or 6 times before it finally reaches the Atlantic. The air in the Amazon is thick. It clings to your skin like a second layer of clothing, warm and wet and heavy. The smell is overwhelming. Rotting fruit, blooming orchids, wet leaves, fungal spores, and the faint sweet stink of decomposition. Everything here is either growing or dying, often simultaneously. The sounds are layered insect hums, bird calls, the distant crash of a falling branch, the constant drip and patter of water moving through the canopy. The Amazon teaches us that life is not a balance but a cycle, that creation and destruction are not opposites but partners, that the forest does not produce oxygen for our benefit but is a byproduct of its own relentless, chaotic, beautiful existence. We are not the center of this story. We are barely a footnote. The rain falls. The trees drink. The water rises again as mist. The cycle continues, indifferent and eternal, as it has since the continents split and the forests claimed the equator. The oldest living tree on Earth is a bristlecone pine named Methuselah, located somewhere in California's White Mountains. It is 4,855 years old. It was already ancient when the pyramids were built. It has lived through the entire span of recorded human history and then some. Its exact location is kept secret to protect it from vandalism, but even if you stood before it, you might not recognize it as remarkable. Bristlecone pines grow slowly, twisted and gnarled by wind and cold, their bark stripped away in places to reveal smooth golden wood beneath. They do not look majestic, they look like survivors. The wood of a bristlecone pine is incredibly dense, almost petrified, and it smells faintly of resin, sharp, clean, medicinal. The needles are short and stiff, dark green, and they remain on the branches for decades. The wind at high altitude is constant and cold, carrying the scent of stone and snow. There is little else here. No undergrowth, no animals, just the pines and the rocks and the sky. What does it mean to survive for 5,000 years? To outlast empires, languages, entire ways of being human? The bristlecone pine does not answer. It simply endures. It teaches us that survival is not about strength or speed, but about patience, about adapting to the harshest conditions and refusing to let go. The tree does not thrive. It persists, and persistence, it turns out, is enough. The wind blows, the tree bends but does not break. The years pass, uncounted and uncountable. The tree stands. When a tree falls in an old-growth forest, it does not die. It transforms. The fallen trunk becomes a nurse log, a horizontal garden where mosses, ferns, fungi and seedlings take root. The decaying wood provides nutrients for decades, sometimes centuries, slowly breaking down into soil that will feed the next generation of trees. In the Pacific Northwest, you can see entire rows of trees growing in perfect lines, their roots straddling the ghost of a nurse log that rotted away long ago. The forest remembers its dead by giving them new life. The smell of a nurse log is rich and complex: wet wood, mushrooms, moss, and the faint sweetness of decay. The bark is soft and spongy, crumbling under your fingers, and the wood beneath is dark and damp, riddled with insect tunnels and fungal threads. The surface is a tapestry of green moss, lichen, ferns, and if you kneel close, you can hear the faint rustle of beetles and millipedes moving through the rot. Death is not an ending here. It is a transformation, a redistribution of energy and matter, a passing of the torch from one generation to the next. The nurse log teaches us that decay is not failure but generosity, that the forest does not waste anything, that every ending is also a beginning. The log lies still, the moss grows, the seedlings reach for light. The forest continues, patient and unhurried, as it always has. The canopy of a tropical rainforest is one of the most biodiverse places on Earth, and yet it is almost entirely inaccessible to humans. Most of the life in a rainforest happens 100 feet above the ground, in a layer of leaves and branches so dense that it blocks out 98% of the sunlight. Scientists estimate that we have catalogued less than 10% of the species living in the canopy. There are entire ecosystems up there: frogs that never touch the ground, plants that grow only on other plants, insects that have never been seen by human eyes. The canopy smells different from the forest floor. The air is lighter, warmer, tinged with the scent of flowers and fruit and the faint, acrid smell of bird droppings. The leaves rustle constantly, a sound like distant applause. And the light is dappled and green, filtered through layer upon layer of foliage. Occasionally a bird calls, sharp and sudden, and then the rustling resumes. The canopy reminds us that the world is larger and stranger than we can imagine, that there are places we will never fully explore, lives we will never fully understand. It teaches humility. It teaches wonder. It teaches us that the forest does not exist for our discovery, that it was here long before us and will be here long after, indifferent to our curiosity. The leaves sway. The light shifts. The unseen creatures move through their unseen lives. The canopy breathes vast and secret and alive. A single leaf is a chemical factory. It takes sunlight, carbon dioxide and water and transforms them into sugar and oxygen through a process so elegant and efficient that human technology has yet to replicate it. Photosynthesis is the foundation of nearly all life on Earth. Every breath you take, every calorie you consume, every living thing you have ever seen, all of it traces back to a leaf, somewhere, turning light into life. A leaf in your hand is almost weightless, thin as paper, and it smells green. A sharp, fresh scent, that fades quickly once the leaf is detached from the tree. The surface is smooth or waxy, or slightly fuzzy, depending on the species, and if you hold it up to the light, you can see the veins branching like rivers, carrying water and nutrients to every cell. The underside is often paler, dotted with tiny pores called stomata, invisible to the naked eye but essential to the leaf's work. The leaf does not labour, it does not struggle, it simply exists in the light, and in existing, it transforms the world. It teaches us that the most profound work is often the quietest, that creation does not require noise or drama, that a single leaf, unremarkable and easily overlooked, is performing a miracle every second of every day. The sun rises. The leaf turns toward it. The sugar flows. The oxygen drifts away. The world continues, sustained by a billion leaves, each one a quiet engine of life. The boreal forest, also called the taiga, is the largest terrestrial biome on Earth, stretching in a vast green belt across Canada, Scandinavia, and Russia. It is a forest of conifers, spruce, pine, fir, adapted to long, brutal winters and short, intense summers. The trees grow slowly here, their wood dense and resinous, their needles designed to conserve water in a landscape where water is often locked away as ice. The boreal forest is not as biodiverse as a rainforest, but it is no less vital. It stores more carbon than any other biome, locking away centuries of atmospheric CO2 in its soil and wood. The air in a boreal forest is cold and clean, scented with pine resin and the faint mineral smell of snow. The ground is carpeted with needles, soft and springy underfoot, and the silence is profound. In winter, the only sounds are the creak of frozen branches and the occasional crack of ice. In summer, the forest hums with mosquitoes and the distant calls of ravens. The boreal forest teaches us that life adapts, that beauty is not always lush or colourful, that survival in the harshest places requires patience and resilience. The trees here do not grow tall or fast, but they grow. They endure. They hold the carbon that would otherwise warm the world. They stand quiet and unnoticed, doing the work that keeps the planet habitable. The wind moves through the pines. The needles whisper. The forest stands, cold and patient, as it has for 10,000 years. The fig tree and the fig wasp are locked in a relationship so intimate that neither can survive without the other. The wasp pollinates the fig, and the fig provides a nursery for the wasp's larvae. This is not cooperation, it is coevolution, a partnership refined over millions of years until the two species are functionally inseparable. There are over 700 species of figs, and each one has its own species of wasp. Remove the wasp, and the fig cannot reproduce. Remove the fig, and the wasp goes extinct. The fig itself is not a fruit, but a flower turned inside out, a hollow chamber lined with tiny blossoms. When you bite into a fresh fig, the texture is soft and grainy, the taste sweet and faintly floral, and the scent is rich and honeyed. Inside, if you look closely, you might see the remains of the wasp that pollinated it, dissolved and absorbed into the fruit's flesh. The fig and the wasp teach us that life is not a collection of isolated individuals, but a web of dependencies, that survival is a collaborative effort, that the boundaries between self and other are often blurred beyond recognition. The forest is full of such partnerships, each one a small miracle of adaptation and trust. The fig ripens, the wasp enters, the cycle continues, ancient and precise, as it has since the age of the dinosaurs. Silence in a forest is never true silence. If you sit still long enough, you begin to hear the layers, the rustle of leaves, the creak of branches, the distant call of a bird, the hum of insects, the whisper of wind. And beneath all of that, if you listen carefully, you can hear the forest itself, the slow movement of sap through wood, the expansion and contraction of bark, the roots drinking from the soil. The forest is always speaking. We have simply forgotten how to listen. The forest floor is soft. The air is cool. The light is green and gold. Time slows. Your breath slows. The forest does not ask anything of you. It simply is, and in its being, it offers a kind of peace that cannot be found anywhere else. The ancient cathedral does not preach. It does not demand belief. It stands, patient and eternal, and it waits. It has been waiting for 400 million years, since the first forests colonized the land and turned the sky blue. It will wait a little longer. The trees stand. The light filters down. The forest breathes. And somewhere, deep in the wood, a seed splits open and begins to grow. The ocean does not begin at the shore. It begins in the darkness, miles below the surface, where the pressure would crush your bones to powder and the cold would stop your heart in seconds. This is the abyssal zone, a realm so alien that we have better maps of Mars than we do of the seafloor. More than 80% of the ocean remains unexplored, unmapped, unseen by human eyes. The deep does not care about our curiosity. It keeps its secrets. The abyssal plains are the flattest places on Earth, stretching for thousands of miles in near-perfect darkness. The pressure here exceeds 8 tons per square inch. No sunlight penetrates this deep. Photosynthesis is impossible, and yet life persists. Strange, slow-moving creatures drift through the black, translucent jellyfish, blind fish, spider-like crabs with legs spanning 10 feet. They do not hunt with eyes. They sense vibrations, chemical trails, the faint bioluminescent flickers of other creatures. If you could somehow survive the descent, the water would feel thick against your skin, dense and cold as liquid stone. There is no smell here, no taste, only pressure and darkness. The silence is absolute, broken occasionally by the creak and groan of shifting sediment, the distant rumble of underwater landslides, the faint clicks and pulses of creatures communicating in frequencies we barely understand. What does it mean to live in a place where light has never reached, where the sun is a myth, a distant rumor from the surface world? The creatures of the abyss do not know day or night, summer or winter. They exist in a timeless present, unchanging and patient, adapted to conditions that would annihilate us in moments. They teach us that life does not require comfort. It requires only persistence. The water presses down. The darkness is complete. The creatures drift, slow and silent. Time dissolves. The Mariana Trench is the deepest point in the ocean, plunging nearly 7 miles below the surface. If you placed Mount Everest at the bottom of the trench, its peak would still be more than a mile underwater. In 1960, 2 men descended to the bottom in a submersible called the Trieste. They reported seeing a flatfish and a shrimp. Life, even here, in the most extreme environment on Earth. The walls of the trench are steep and barren, coated in fine sediment that has drifted down over millions of years. The water is near freezing, just above the point where it would turn to ice under the immense pressure. There is no current here, no movement, only the slow, patient accumulation of debris from the world above. The trench teaches us that there is no place on Earth too hostile for life, that the boundaries we imagine, too deep, too cold, too dark, are human constructs, irrelevant to the organisms that have spent millions of years adapting to the impossible. Life does not ask permission. It simply finds a way. The pressure mounts. The darkness deepens. The trench waits, silent and patient, as it has since the Pacific Plate began its slow descent beneath the Philippine Plate 50 million years ago. Bioluminescence is the ocean's language. In the deep, where no sunlight reaches, creatures generate their own light through chemical reactions in specialized cells. Some use it to lure prey, dangling glowing appendages like fishing lures. Others use it to communicate, flashing patterns that signal mating readiness or territorial warnings. Still others use it as camouflage, matching the faint downwelling light from above to erase their silhouettes from predators below. The light is cold and blue-green, eerie and beautiful, like distant stars reflected in water. It does not illuminate the surroundings. It only marks the presence of the creature producing it. The flashes are brief, lasting seconds or less, and then the darkness returns, deeper than before. Bioluminescence reminds us that light is not a given, that in the absence of the sun, life invents its own solutions, that beauty exists even in the darkest places. The deep ocean glows with a light that no human eye was meant to see, a light that has been flickering in the darkness for hundreds of millions of years. The creatures flash, the light pulses, the darkness swallows it. The ocean continues, patient and indifferent. Hydrothermal vents are cracks in the ocean floor where superheated water, sometimes exceeding 700 degrees Fahrenheit, erupts from the Earth's crust. The water is laden with minerals, sulfur, iron, copper, zinc. When it meets the frigid ocean water, the minerals precipitate out, forming towering chimneys called black smokers. Around these vents, entire ecosystems thrive, powered not by sunlight but by chemosynthesis, bacteria that convert the chemicals in the vent water into energy. The water near a vent shimmers with heat, and the smell, if you could somehow smell it, would be sulphurous like rotten eggs, sharp and acrid. The chimneys are black and jagged, crusted with minerals, and the water pouring from them is opaque, thick with dissolved metals. Around the vents, giant tube worms sway in the current, their red plumes filtering bacteria from the water. Eyeless shrimp cluster by the thousands, their bodies pale and ghostly. The vents teach us that life does not require the sun, that the energy for existence can come from the earth itself, that the rules we thought were universal, photosynthesis, the food chain, the dependence on light, are merely local customs, irrelevant in the deep. The vents are a glimpse of what life might look like on other worlds, in oceans beneath the ice of Europa, or Enceladus. The water boils. The minerals precipitate. The bacteria thrive. The vents hiss and steam, indifferent to the cold and the dark. The ocean is not silent. It is filled with sound, the songs of whales, the clicks of dolphins, the snaps of shrimp, the low-frequency rumble of earthquakes and underwater volcanoes. Sound travels faster and farther in water than in air, and the ocean acts as a vast acoustic chamber, carrying whale songs across entire ocean basins. A blue whale's call at frequencies below human hearing can be detected thousands of miles away. The songs are haunting, rising and falling in slow, mournful arcs. They are not random. They have structure, rhythm, patterns that change over time, suggesting something like culture, like learning, like art. The whales do not sing for us. They sing for each other, across distances we can barely comprehend. The songs remind us that intelligence takes many forms, that communication does not require language, that the ocean is not empty but filled with voices, with stories, with lives as complex and meaningful as our own. We are not the only ones who sing. The whales call, the ocean carries their voices. The songs echo across the deep, patient and timeless. Coral reefs cover less than 1% of the ocean floor, yet they support roughly 25% of all marine species. They are the rainforests of the sea, built not by plants but by tiny animals called polyps. Each polyp secretes a calcium carbonate skeleton, and over centuries, these skeletons accumulate into massive structures, reefs that can be seen from space. The Great Barrier Reef, the largest living structure on Earth, stretches for more than 1,400 miles along the coast of Australia. The reef is a riot of colour and texture. branching corals like antlers, brain corals with their convoluted surfaces, soft corals swaying in the current. The water is warm and clear, and the smell, if you surface nearby, is salty and faintly organic, like seaweed drying in the sun. Fish dart through the coral, their scales flashing in the sunlight, and the reef itself hums with the sound of parrotfish crunching coral, shrimp snapping their claws, waves breaking overhead. The reef teaches us that small actions repeated over time can build something vast and enduring, that collaboration between polyps and their symbiotic algae, between the reef and the creatures that depend on it, is the foundation of resilience. The reef is fragile and ancient, beautiful and vulnerable, a reminder that even the most enduring structures can be destroyed. The polyps build, the reef grows, the ocean breathes. The cycle continues. The ocean's twilight zone, also called the mesopelagic, extends from about 600 to 3,000 feet below the surface. This is the realm of fading light, where the sun's rays weaken to a dim blue glow before disappearing entirely. It is home to the largest migration on Earth, not of birds or mammals, but of fish, squid, and zooplankton. Every night, billions of creatures rise from the depths to feed in the nutrient-rich surface waters. Every dawn, they descend again, a vertical journey that can span hundreds of feet. The water here is cold and dim, tinted blue-grey, and the creatures are strange. Hatchetfish with upward-facing eyes, lanternfish covered in bioluminescent spots, squid with tentacles longer than your arm. The light from above is faint, barely enough to see by, and the pressure is building, a constant weight against your chest. The migration teaches us that survival often requires movement, that safety and food are rarely found in the same place, that the ocean is not a static environment but a dynamic, shifting world where creatures must adapt or perish. The twilight zone is a place of transition, of change, of creatures caught between the light and the dark. The sun sets, the creatures rise, the ocean shifts. The migration continues, ancient and relentless. Kelp forests are underwater cathedrals, towering groves of brown algae that can grow more than 2 feet per day, reaching heights of over 100 feet. The kelp anchors itself to rocky seafloors with root-like structures called holdfasts, and its long, flexible stipes sway in the current like trees in the wind. The canopy floats at the surface, buoyed by gas-filled bladders, creating a dense, sunlit layer where fish, sea otters, and invertebrates thrive. The water in a kelp forest is cool and green-tinted, filtered through layers of swaying fronds. The kelp itself smells faintly of iodine and salt, and the holdfasts are rough and textured, encrusted with barnacles and small crabs. The forest is alive with sound, the rustle of kelp in the current, the crack of sea urchins grazing on the stipes, the distant bark of sea lions. The kelp forest teaches us that growth is not always slow, that some organisms can transform their environment in days rather than decades, that the ocean is not a desert, but a garden, constantly renewing itself. The kelp does not last forever. Storms tear it away, urchins devour it. But it always returns, patient and persistent. The kelp sways, the current flows, the forest breathes, the ocean continues. The ocean absorbs roughly 30% of the carbon dioxide we release into the atmosphere, acting as a vast carbon sink that slows the pace of climate change. But this comes at a cost. When CO2 dissolves in seawater, it forms carbonic acid, lowering the ocean's pH in a process called ocean acidification. The water becomes more corrosive, making it harder for creatures like corals, mollusks, and plankton to build their calcium carbonate shells and skeletons. The acidified water does not look different. It does not smell different. The change is invisible, measurable only with instruments, and yet it is reshaping the ocean at a fundamental level. The creatures affected do not understand what is happening. They simply struggle to build, to grow, to survive. Ocean acidification teaches us that invisible changes can have profound consequences, that the ocean is not infinite or invulnerable, that our actions ripple outward in ways we cannot always see. The ocean has absorbed our carbon for centuries, buffering us from the worst effects of our own emissions. But every buffer has a limit. The ocean absorbs, the pH drops, the creatures struggle, the water continues, patient but not infinite. The ocean's surface is a boundary, a membrane between two worlds. Above, air and light and the familiar rhythms of terrestrial life. Below, pressure and darkness and alien forms. The surface is where these worlds meet, where waves break and seabirds dive and sunlight penetrates just deep enough to fuel the phytoplankton that form the base of the marine food web. The surface is not a place but a transition, a threshold, a skin stretched over the deep. The surface smells of salt and spray, and the air is cool and damp. The water is restless, never still, rising and falling with the breath of the wind. The light dances on the waves, fracturing into 1,000 glittering shards, and beneath, the blue deepens, darkens, becomes impenetrable. The surface teaches us that boundaries are not walls, but membranes, that the world is not divided into separate realms, but connected by transitions, by gradients, by places where one thing becomes another. The ocean does not end at the shore, it begins there. The waves rise, the light dances, the boundary holds, the ocean breathes. In the deepest parts of the ocean, time moves differently. A glass sponge can live for 15,000 years, filtering nutrients from the water with a patience that makes redwoods look hurried. A Greenland shark can live for 400 years, swimming slowly through the Arctic waters, growing less than half an inch per year. These creatures do not experience time the way we do. They do not count days or years. They simply exist, slow and patient, outlasting empires and ice ages. The deep is cold and still. The creatures move slowly, conserving energy in an environment where food is scarce and every calorie counts. The sponges do not move at all. They anchor to the seafloor and wait, filtering the water, growing imperceptibly, accumulating centuries like dust. The deep teaches us that time is not a constant, that the pace of life is not universal, that patience is not passive, but a form of endurance, a strategy for survival in a world that does not reward haste. The deep does not hurry, it has no reason to. The sponge filters, the shark drifts, the centuries pass. The deep remains, patient and timeless. The ocean is the source of all life on Earth. The first cells emerged in warm, shallow seas more than 3.5 billion years ago. For billions of years, life existed only in the ocean. The land was barren, lifeless, scoured by radiation and wind. It was the ocean that nurtured the first photosynthetic bacteria, the first multicellular organisms, the first fish that crawled onto land and became the ancestors of every terrestrial creature alive today. We are all children of the sea. The ocean does not remember this. It does not take pride in its role as the cradle of life. It simply continues, vast and indifferent, its currents circulating, its tides rising and falling, its depths concealing mysteries we may never fully understand. The ocean teaches us humility. It teaches us that we are not separate from nature but part of it, that our history is written in salt water and ancient genes, that the blue world beneath the waves is not a foreign place, but our oldest home. The tides turn, the currents flow, the ocean breathes, and somewhere in the deep, life continues, patient and eternal, as it has since the beginning. The diamond in your hand was once carbon, buried deep beneath the Earth's surface, subjected to pressures exceeding 700,000 pounds per square inch, and temperatures hot enough to melt rock. It took billions of years to form, and it will last billions more. The diamond does not care about its beauty or its value. It is simply the inevitable result of carbon atoms arranged in the most stable configuration possible under extreme conditions. Pressure transforms, time crystallizes, the Earth creates jewels in its depths. Diamonds form in the mantle, 90 to 120 miles below the surface, where the pressure is so intense that carbon atoms lock into a rigid three-dimensional lattice. Volcanic eruptions bring them to the surface in pipes of kimberlite rock, blasting upward at speeds exceeding 200 miles per hour. Most diamonds are billions of years old, formed when the Earth was young and violent. A diamond is cold to the touch, impossibly hard, and it refracts light into rainbows. It has no smell, no taste, only geometry and clarity. When you hold one up to the light, it fractures the world into 1,000 glittering facets, each one a window into deep time. The diamond teaches us that beauty is often born from violence, that the most enduring things are forged under the greatest pressure, that transformation requires both force and time. The Earth does not create gently. It crushes and heats and waits, and what emerges is harder than anything on the surface. The pressure mounts, the carbon crystallizes, the diamond waits, patient and eternal, buried in the dark. Quartz is the second most abundant mineral in the Earth's continental crust, and it comes in more varieties than almost any other mineral. Clear rock crystal, purple amethyst, pink rose quartz, yellow citrine, smoky quartz, all of them are silicon dioxide, arranged in the same hexagonal crystal structure. But trace impurities and radiation exposure create the colors. Quartz is piezoelectric. It generates an electric charge when compressed. This property makes it essential for watches, radios, and computers. Quartz crystals grow slowly, atom by atom, in cavities within cooling magma or in hydrothermal veins where mineral-rich water seeps through cracks in the rock. The crystals are hexagonal, often terminating in perfect pyramidal points, and they feel smooth and cool, like glass. When struck together, two pieces of quartz produce a faint spark and a sharp, clean sound. Quartz teaches us that structure determines function, that the same elements arranged differently create entirely different properties, that the Earth is an alchemist, transmuting simple ingredients into complexity. The crystal does not know it is beautiful. It simply grows, following the laws of geometry and chemistry. The atoms align. The crystal grows, the structure holds. Time passes, measured in the vibrations of silicon and oxygen. Obsidian is volcanic glass, formed when lava cools so quickly that crystals do not have time to form. The result is a rock that is not technically a rock at all, but a frozen liquid, smooth and glassy and sharp enough to cut at the molecular level. Ancient peoples used obsidian for tools and weapons, and modern surgeons sometimes use obsidian scalpels because the edge is finer than steel. Obsidian is black and glossy, reflecting light like a dark mirror. It fractures in smooth conchoidal curves, and the edges are so sharp that they can slice through skin without you feeling it. The surface is cool and slick, and it has no smell, no texture beyond its glassy smoothness. Obsidian teaches us that speed matters, that the same material can become entirely different depending on how quickly it cools, that the Earth's processes are not always slow and patient. Sometimes transformation happens in an instant, and what emerges is something unexpected, something sharp and strange and beautiful. The lava erupts, the air cools it, the glass forms black and sharp and frozen in time. Geodes are hollow rocks lined with crystals, formed when mineral-rich water seeps into cavities in volcanic or sedimentary rock and slowly deposits layers of quartz, calcite, or other minerals. From the outside, a geode looks like an ordinary rock, rough, brown, unremarkable. But crack it open, and the interior is a cathedral of crystals, glittering and geometric, a hidden world that took millions of years to build. The crystals inside a geode are often purple amethyst or clear quartz, and they catch the light in a way that makes the hollow interior seem to glow. The surface of the crystals is smooth and faceted, and the air inside smells faintly mineral, like wet stone. The geode is heavy, denser than it looks, and when you shake it, you can sometimes hear loose fragments rattling inside. The geode teaches us that beauty is often hidden, that the most extraordinary things are not always visible from the outside, that patience and time can create wonders in the dark. The geode does not advertise its contents. It waits to be discovered. The water seeps, the minerals precipitate, the crystals grow, hidden and patient in the dark. Limestone is the compressed remains of ancient sea creatures, billions upon billions of shells, skeletons and coral fragments, compacted over millions of years into solid rock. Most of the world's limestone formed in warm, shallow seas during the Mesozoic and Paleozoic eras, when the oceans teemed with life. The rock is soft enough to carve, and it has been used for millennia to build temples, pyramids, and cathedrals. Limestone is pale grey or white, sometimes tinged with yellow or pink, and it feels chalky and slightly gritty. When you scratch it, it leaves a white powder on your fingers, and it smells faintly of the sea, a mineral tang that hints at its origins. In places, you can see the fossils embedded in the rock, spiraled shells, branching corals, the delicate imprints of ancient creatures. Limestone teaches us that the past is not gone but transformed, that the creatures of ancient oceans are still here, holding up our buildings and paving our roads, that death is not an ending but a contribution to the future. The limestone remembers the sea, even though the sea is long gone. The shells accumulate, the pressure mounts, the rock forms pale and patient, holding the memory of ancient oceans. Granite is the foundation of continents, the bedrock upon which mountains and cities are built. It forms deep underground when magma cools slowly, allowing large crystals of quartz, feldspar and mica to grow. The result is a rock that is hard, durable, and speckled with colour: grey, pink, black, white. Granite weathers slowly, resisting erosion for millions of years, and when it finally does erode, it becomes sand. Granite is rough and granular, and it feels solid in a way that few other rocks do. The crystals are visible to the naked eye, each one a tiny facet catching the light. The rock is cool and heavy, and it smells faintly of dust and minerals. When you strike it with a hammer, it rings with a clear, sharp sound. Granite teaches us that strength comes from structure, that the slow formation of interlocking crystals creates something nearly indestructible, that the earth builds its foundations with patience and precision. The granite does not hurry. It cools slowly, crystallizes slowly, and endures. The magma cools. The crystals grow, the granite solidifies, hard and patient beneath the surface. Salt crystals form when seawater evaporates, leaving behind sodium chloride in perfect cubic structures. The crystals grow in layers, stacking atom by atom, and they are so regular, so geometrically precise, that they seem almost artificial. Salt has been essential to human civilization for millennia, used to preserve food, to flavor meals, to pay wages. The word salary comes from the Latin word for salt. Salt crystals are white or translucent, and they catch the light in a way that makes them sparkle. They feel dry and slightly rough, and they dissolve instantly on your tongue, releasing a sharp, clean taste. The smell is faintly mineral, like the ocean on a hot day. Salt teaches us that necessity and beauty are not opposites, that the most essential things can also be elegant, that the earth provides what we need in forms that are both functional and exquisite. The salt does not know it is valuable, it simply crystallizes, following the laws of chemistry. The water evaporates, the salt remains. The crystals form, white and perfect, in the sun. Marble is limestone that has been transformed by heat and pressure deep within the Earth's crust. The process, called metamorphism, recrystallizes the calcite, creating a rock that is harder, denser, and more beautiful than the original. Marble has been prized for sculpture and architecture for thousands of years. Michelangelo carved David from a single block of Carrara marble, and the Parthenon was built from Pentelic marble. Marble is smooth and cool with a faint translucency that allows light to penetrate the surface. The colors range from pure white to veined with grey, green, pink or gold, and the surface polishes to a high gloss. When you run your hand over it, it feels almost soft despite its hardness, and it smells faintly of stone and dust. Marble teaches us that transformation is not destruction but refinement, that pressure and heat can take something ordinary and make it extraordinary, that the earth is an artist, sculpting and polishing and creating beauty from raw materials. The marble does not resist the transformation, it simply becomes. The heat rises, the pressure mounts, the limestone transforms, becoming marble, smooth and luminous. Fossils are the Earth's memory, the preserved remains of organisms that lived millions of years ago. Most fossils form when an organism is buried quickly in sediment, protecting it from decay. Over time, minerals seep into the bones or shells, replacing the original material atom by atom, until what remains is a stone replica, perfect in every detail. Fossils are not the organisms themselves, but their echoes, their shadows cast in rock. Fossils feel like stone because they are stone, but they retain the shape and texture of the original organism. A fossilized shell is smooth and spiraled. A dinosaur bone is porous and textured. A leaf imprint is delicate and detailed. They smell of earth and minerals, and they are heavy, denser than the living tissue they once were. Fossils teach us that the past is not lost, that the earth keeps records, that time does not erase but transforms. The fossils do not speak, but they tell stories of ancient seas, of forests that no longer exist, of creatures that walked the earth long before we did. The organism dies, the sediment buries it, the minerals replace it. The fossil remains, a memory in stone. Stalactites and stalagmites form in caves when water, laden with dissolved calcium carbonate, drips from the ceiling. Each drop leaves behind a tiny deposit of mineral, and over thousands of years, these deposits accumulate into hanging icicles of stone, stalactites, or rising pillars, stalagmites. The formations grow at a rate of less than a millimeter per year, and some are hundreds of thousands of years old. The stone is smooth and wet, often tinged with orange or brown from iron impurities, and it glistens in the dim light of the cave. The air smells of damp earth and minerals, and the only sound is the slow, rhythmic drip of water, each drop a tiny contribution to the growing formation. Stalactites and stalagmites teach us that even the smallest actions, repeated over time, can build something monumental. That patience is the most powerful force in nature, that the earth does not hurry, the formations do not rush. They grow, drop by drop, in the darkness. The water drips, the mineral deposits, the stone grows, slow and patient, in the cave. Petrified wood is wood that has turned to stone, a process that occurs when a tree is buried in sediment and mineral-rich water replaces the organic material cell by cell. The result is a fossil that retains the exact structure of the original wood, the grain, the rings, even the texture of the bark, but is now made entirely of stone, often quartz or chalcedony. Petrified wood can be millions of years old, Petrified wood is heavy and hard, and it feels like stone. But when you look closely, you can see the wood grain, the growth rings, the knots and imperfections. The colours are often vibrant: reds, yellows, blues, greens, created by different minerals. It smells of earth and stone, with no trace of the tree it once was. Petrified wood teaches us that transformation is complete, that the past can be preserved in forms we do not expect, that the earth is patient enough to turn wood into stone, cell by cell, over millions of years. The tree is gone, but its shape remains, immortalized in rock. The tree falls, the sediment buries it, the minerals replace it, the wood becomes stone, patient and eternal. Crystals grow according to strict geometric rules, their atoms arranging themselves in repeating patterns that create the shapes we recognize: hexagons, cubes, pyramids, prisms. The shape of a crystal is not random but determined by the internal structure of its atoms. A snowflake is a crystal of ice, and no two are exactly alike, but all are hexagonal because water molecules bond at 120-degree angles. Crystals are smooth and faceted, and they catch the light in ways that seem almost magical. They feel cool and solid, and they have no smell, only geometry and clarity. When you hold a crystal up to the light, it refracts and reflects, breaking the light into colors and patterns. Crystals teach us that order emerges from chaos, that the universe follows rules, that beauty is not arbitrary but mathematical, that the same laws that govern atoms also govern galaxies. The crystal does not choose its shape. It simply grows, following the geometry encoded in its structure. The atoms align. The crystal grows. The geometry manifests. The pattern repeats, perfect and eternal. The wind does not begin where you feel it. It begins thousands of miles away, born from differences in temperature and pressure, from the uneven heating of the Earth's surface by the sun. Air rises over the equator, cools and sinks at the poles, and the planet's rotation twists these currents into the trade winds, the westerlies, the jet streams. The wind you feel on your face today may have started its journey over the Pacific Ocean, carrying with it the memory of waves and salt spray. Wind is invisible, known only by its effects: the rustling of leaves, the bending of grass, the ripples on water. It has no color, no form, only movement and sound. When it blows through a canyon, it howls. Through a forest, it whispers. Across an open plain, it roars. The air smells different depending on where the wind has been. Ocean winds carry salt, desert winds carry dust, mountain winds carry the scent of pine and snow. The wind teaches us that influence does not require visibility, that the most powerful forces are often the ones we cannot see, that movement is a form of connection, linking distant places and distant times. The wind does not care where it goes. It simply moves, carrying heat and moisture and seeds and stories across the face of the earth. The air moves. The pressure shifts. The wind blows, patient and relentless, as it has since the earth first had an atmosphere. Stars are not eternal. They are born in clouds of gas and dust, live for millions or billions of years, and die in explosions or slow fades, depending on their mass. Our sun is middle-aged, about 4.5 billion years old, with another 5 billion years left before it swells into a red giant and consumes the inner planets. The light you see from distant stars is ancient. Some of those stars may already be dead, their light still travelling across the void. Starlight is cold and distant, a pinprick of white or blue or red against the black. The stars do not twinkle in space, only in our atmosphere, where turbulence bends the light. On a clear night, far from city lights, the sky is so full of stars that it seems almost crowded, and the Milky Way stretches overhead like a river of light. The stars teach us that time is not what we think it is, that the past and present exist simultaneously depending on where you stand, that light is both a messenger and a memory. The stars do not shine for us. They shine because fusion in their cores converts hydrogen to helium, releasing energy that takes thousands of years to reach the surface and then 8 minutes to reach Earth. The stars burn, the light travels, the sky remembers, holding the past in every photon. The aurora's northern and southern lights are caused by charged particles from the sun colliding with gases in Earth's atmosphere. The particles follow the planet's magnetic field lines toward the poles, where they excite oxygen and nitrogen atoms, causing them to glow. Oxygen produces green and red light, nitrogen produces blue and purple. The result is a shimmering curtain of colour that dances across the polar skies. The auroras move like living things, rippling and folding, brightening and fading. The colours are ethereal, pale greens, deep purples, occasional reds, and they reflect off snow and ice, doubling their intensity. The air is cold and still, and the only sound is the crunch of snow underfoot, and occasionally a faint crackling that some people claim to hear when the auroras are particularly strong. The auroras teach us that beauty often emerges from collision, that the Earth is not isolated but constantly bombarded by particles from the sun, that our planet's magnetic field is both a shield and a canvas. The auroras do not perform for us. They are simply the visible evidence of invisible forces. The particles collide, the atoms glow. The sky dances, silent and luminous, in the polar night. Clouds are not solid. They are collections of water droplets or ice crystals so small that they remain suspended in the air, held aloft by updrafts and air currents. A single cumulus cloud can weigh more than 1 million pounds, yet it floats because the droplets are dispersed over a vast volume. Clouds form when warm, moist air rises and cools, and the water vapor condenses around tiny particles of dust or salt. Clouds feel damp when you walk through them. Fog is simply a cloud at ground level. They smell clean and fresh, like rain about to fall, and they taste faintly mineral if you catch the droplets on your tongue. The light inside a cloud is diffuse and grey, and the world beyond disappears, leaving only whiteness and the sound of your own breathing. Clouds teach us that weight is relative, that what seems solid is often mostly empty space, that the sky is not a void but a dynamic, shifting realm where water cycles endlessly between liquid, vapor and ice. The clouds do not rest. They form, drift and dissipate, part of a cycle that has no beginning and no end. The air rises. The vapor condenses, the cloud forms, white and weightless, drifting across the sky. The moon does not produce its own light, it reflects the sun's light. And the phases we see, new moon, crescent, half gibbous, full, are simply the changing angles between the sun, earth, and moon. The moon is slowly drifting away from Earth at a rate of about 1.5 inches per year, a consequence of tidal forces. Billions of years ago, the moon was much closer and the days were shorter. The moon's surface is grey and cratered, scarred by billions of years of asteroid impacts. It has no atmosphere, no weather, no erosion beyond the slow sandblasting of micrometeorites. The light it reflects is cold and silver, casting sharp shadows and turning the landscape into a study in contrasts, black and white, light and dark. The moon teaches us that presence does not require activity, that influence can be exerted across vast distances, that the tides in our oceans are pulled by a rock 250,000 miles away. The moon does not change. It simply orbits, patient and constant, as it has since it formed from the debris of a collision between Earth and a Mars-sized object 4.5 billion years ago. The moon orbits, the light reflects, the tides rise and fall, governed by a distant companion. Lightning is a discharge of electricity between a cloud and the ground, or between two clouds, caused by the buildup of static charge from colliding ice particles. A single bolt can carry up to 1 billion volts and heat the air to 50,000 degrees Fahrenheit, 5 times hotter than the surface of the sun. The superheated air expands explosively, creating the sound we call thunder. Lightning is jagged and brilliant, branching across the sky in fractal patterns that last less than a second. The light is white or blue-white, so bright that it leaves afterimages on your retinas. The air smells sharp and clean after a lightning strike. Ozone, created when the electricity splits oxygen molecules. Thunder rumbles and cracks, echoing across the landscape. Lightning teaches us that the sky is not calm, that the atmosphere is charged with energy, that the same forces that power our electronics also split the sky in moments of violent beauty. Lightning does not discriminate. It strikes the tallest object, the path of least resistance, indifferent to what it hits. The charge builds, the bolt strikes, the sky splits, bright and sudden, and the thunder follows. Rainbows are not objects, but optical phenomena created when sunlight is refracted, reflected, and dispersed by water droplets in the air. Each droplet acts as a tiny prism, splitting white light into its component colors: red, orange, yellow, green, blue, indigo, violet. The rainbow you see is unique to your position. Someone standing next to you sees a slightly different rainbow, formed by different droplets. A rainbow is ephemeral, lasting only as long as the conditions that create it, sun and rain at the same time. The colors are soft and luminous, arcing across the sky, and they fade at the edges, blending into the surrounding air. There is no pot of gold at the end because there is no end. The rainbow is a circle, and we see only the arc above the horizon. Rainbows teach us that beauty is often fleeting, that what we see depends on where we stand, that light contains multitudes. The rainbow does not exist for us. It is simply the consequence of geometry and optics, a reminder that the world is more complex and more beautiful than it appears. The light refracts, the colors separate, the rainbow arcs, brief and luminous, across the rain. The jet stream is a river of air flowing at altitudes of 30 to 40,000 feet, with speeds that can exceed 200 miles per hour. It forms at the boundary between cold polar air and warm tropical air, and it meanders across the planet, influencing weather patterns and steering storms. Pilots use the jet stream to shorten flight times when flying east, and avoid it when flying west. The jet stream is invisible from the ground, but you can see its effects in the movement of clouds and the speed at which weather systems travel. The air at that altitude is thin and cold, and the wind is constant and powerful, a force that shapes the weather for thousands of miles in every direction. The jet stream teaches us that the atmosphere is layered, that the sky is not uniform but stratified into zones with different properties, that the wind at ground level is only a fraction of the movement happening above. The jet stream does not rest. It flows day and night, a river of air circling the globe. The air flows. The stream meanders. The wind blows high and fast, shaping the weather below. Meteors are fragments of rock and metal, debris from comets and asteroids that enter Earth's atmosphere at speeds of up to 45 miles per second. The friction with the air heats them to incandescence, creating the streaks of light we call shooting stars. Most meteors are no larger than a grain of sand, and they burn up completely before reaching the ground. The ones that survive are called meteorites. A meteor is a brief flash of light, white or green or orange, streaking across the sky and disappearing in a second or less. During a meteor shower, dozens or even hundreds can be seen in an hour, all radiating from a single point in the sky. The air is silent. The meteor is too high and too fast to produce sound. Meteors teach us that the solar system is not empty, that space is filled with debris, that the Earth is constantly being bombarded by fragments of the cosmos. Most burn up harmlessly, but occasionally a large one survives, and the impact reshapes the landscape. The meteors do not announce themselves. They simply fall, silent and bright, through the night. The fragment enters. The air heats it. The meteor burns, brief and brilliant, across the dark. The Milky Way is our galaxy, a spiral of 200 billion stars, and we are located about halfway out from the center, in a minor arm called the Orion Spur. On a clear, dark night, far from city lights, you can see the Milky Way as a band of light stretching across the sky, the combined glow of billions of stars, too distant to resolve individually. We are looking at our galaxy edge on, from the inside. The Milky Way is faint and diffuse, a river of light that seems to flow across the sky. The stars are so numerous that they blur together, and the dark patches are not empty, but clouds of dust blocking the light from stars beyond. The sight is humbling, a reminder of scale and insignificance. The Milky Way teaches us that we are part of something vast, that our sun is one star among billions, that the galaxy does not revolve around us but carries us along in its slow rotation, which takes 250 million years to complete. The galaxy does not notice us. It simply turns, patient and immense, as it has since it formed 13 billion years ago. The stars shine. The galaxy turns. The light reaches us, ancient and patient, from across the void. The atmosphere is not uniform. It is layered into distinct zones. The troposphere, where weather happens. The stratosphere, where the ozone layer absorbs ultraviolet radiation. The mesosphere, where meteors burn up. The thermosphere, where the auroras occur, and the exosphere gradually fades into space. Each layer has different properties: temperature, pressure, composition, and they interact in complex ways. The atmosphere is invisible, but you can feel it, the weight of the air pressing down, the resistance when you move through it, the way it carries sound and scent. It smells of whatever it has passed over, ocean, forest, city, and it tastes faintly of oxygen and nitrogen, the gases that make up most of its volume. The atmosphere teaches us that protection comes in layers, that the sky is not a single thing but a series of zones, each one serving a different function, that the air we breathe is part of a system that extends hundreds of miles above our heads. The atmosphere does not rest. It circulates, mixes and protects, a thin shell of gas that makes life possible. The layers stack. The air circulates. The atmosphere holds, fragile and essential, between us and the void. Constellations are patterns we impose on the stars, connecting distant suns into shapes that have meaning only to us. Orion, Ursa Major, Cassiopeia. These are not real structures but accidents of perspective, stars at vastly different distances that happen to align from our point of view. The constellations have changed over time as the stars move through space, and they will change again. The sky is not fixed. The stars of a constellation are white or blue or red, scattered across the black, and the patterns are often difficult to see without practice. The air is cold and still, and the stars do not move, though the Earth's rotation makes them appear to wheel across the sky. Constellations teach us that meaning is something we create, that the universe does not come pre-organized, that the stories we tell about the stars say more about us than about the stars themselves. The constellations do not exist. They are simply the way we make sense of the vastness, the way we find our place in the sky. The stars shine. We connect them. The patterns emerge, human and temporary, against the eternal dark. Mycelium is the hidden half of the fungal kingdom, a network of thread-like filaments called hyphae that spread through soil, wood, and leaf litter. A single teaspoon of healthy forest soil can contain miles of mycelial threads, invisible to the naked eye but essential to the ecosystem. Mycelium breaks down dead organic matter, recycles nutrients and forms partnerships with plant roots, exchanging minerals for sugars. It is the internet of the forest, connecting trees and plants in a web of mutual support. The hyphae are finer than human hair, white or translucent, and they branch and fuse in patterns that resemble neural networks. When you dig into forest soil, you can see them, delicate threads clinging to roots and decomposing leaves. The soil smells rich and earthy, like wet wood and mushrooms, and it feels cool and slightly damp. The mycelium is everywhere, invisible but omnipresent, a living fabric woven through the ground. Mycelium teaches us that what we see above ground is only a fraction of what exists, that the most important work often happens in darkness. That connection is survival. The mycelium does not compete. It collaborates, linking organisms across species boundaries, creating a network that has existed for more than 1 billion years. The hyphae spread, the network grows, the mycelium connects, silent and patient, beneath the surface. Mushrooms are the fruiting bodies of fungi, temporary structures that emerge to release spores and then disappear. The mushroom you see is not the organism itself, but its reproductive organ, like an apple on a tree. The actual fungus is the mycelium beneath the soil, which can live for decades or even centuries. Some fungi produce mushrooms only once every few years, waiting for the perfect conditions: moisture, temperature, nutrients. Mushrooms come in every shape and color: red caps with white spots, delicate white parasols, shelf-like brackets growing from tree trunks, puffballs that release clouds of spores when touched. They smell earthy and sometimes faintly sweet, and their textures range from spongy to firm to brittle. Some are edible, some are poisonous, and many are simply inedible, too tough or too bitter. Mushrooms teach us that what appears suddenly has been preparing for a long time, that emergence is not spontaneous but the result of hidden work, that the visible is only the tip of the invisible. The mushroom does not last. It releases its spores and dissolves, returning to the soil, while the mycelium continues its work below. The conditions align, the mushroom emerges, the spores release. The cycle continues, patient and ancient. The largest living organism on Earth is a fungus. Armillaria ostoyae, also called the honey mushroom, covers more than 2,000 acres in Oregon's Blue Mountains. The mycelium has been growing for an estimated 2,500 years, spreading through the soil and feeding on the roots of trees. Above ground, you would see only scattered clusters of honey-colored mushrooms, but beneath the surface, it is all one organism, genetically identical, connected by a vast network of hyphae. The forest where the fungus grows is quiet and cool, carpeted with pine needles and dotted with stumps of trees the fungus has killed. The air smells of resin and decay, and the mushrooms, when they appear, smell faintly of honey and earth. The mycelium itself is invisible, but its effects are everywhere: dead trees, new growth, the slow recycling of nutrients. The honey mushroom teaches us that size is not always visible, that the largest things are often the quietest, that an organism can be both destroyer and sustainer, killing trees to feed the soil that will grow new trees. The fungus does not hurry. It spreads slowly, patiently across the forest floor. The mycelium spreads. The trees fall. The forest renews. The fungus continues, ancient and vast. Fungi are neither plants nor animals, but a kingdom unto themselves. They do not photosynthesize like plants or hunt like animals. Instead, they secrete enzymes that break down organic matter externally, then absorb the nutrients. This makes them essential decomposers, capable of breaking down everything from dead leaves to oil spills to plastic. Some fungi can even digest rock, extracting minerals and contributing to soil formation. Fungi grow in darkness, in damp places, on rotting wood and fallen leaves. They smell of earth and decay, a rich, complex scent that is neither pleasant nor unpleasant, but simply organic. The textures vary. Some are slimy, some are dry and powdery, some are firm and rubbery. They do not move, but they grow, spreading their hyphae through whatever substrate they inhabit. Fungi teach us that destruction is creation, that decay is not an ending but a transformation, that the nutrients locked in dead matter must be released for new life to begin. Fungi are the alchemists of the natural world, turning death into soil, waste into food, endings into beginnings. The enzymes secrete, the matter breaks down, the nutrients release, the cycle turns, patient and essential. Lichens are not single organisms but symbiotic partnerships between fungi and algae, or cyanobacteria. The fungus provides structure and protection, while the algae or bacteria photosynthesize, producing food for both partners. Lichens can survive in the harshest environments on Earth, on bare rock, in deserts, in the Arctic, even in the vacuum of space. They grow slowly, sometimes less than a millimeter per year, and some are thousands of years old. Lichens come in many forms: crusty patches on rocks, leafy rosettes on tree bark, branching structures that hang from branches like miniature forests. They are grey, green, orange, yellow, white, every colour except blue. They feel dry and papery or slightly rubbery, and they have no smell, or only a faint, dusty scent. When wet, they become soft and pliable, absorbing water like a sponge. Lichens teach us that partnership can create resilience, that two organisms working together can survive where neither could alone, that patience is a form of strength. Lichens do not compete. They colonize, slowly transforming bare rock into soil, preparing the way for other life. The partners merge, the lichen grows, the rock becomes soil. Time passes, measured in millimeters. Mycelium can communicate. When a plant is attacked by insects, it can send chemical signals through the mycorrhizal network to neighboring plants, warning them of the threat. The warned plants then increase their production of defensive chemicals, making themselves less palatable to herbivores. This is not conscious communication, but it is information transfer, a form of language written in molecules and transmitted through fungal threads. The signals are invisible, chemical gradients moving through the soil, and they travel faster than you might expect. Within hours, plants across a network can respond to a threat detected by a single individual. The forest is not silent. It is speaking constantly, in a language we are only beginning to understand. Mycelial communication teaches us that intelligence does not require a brain, that networks can process and transmit information without centralized control, that the forest is not a collection of individuals but a community, interconnected and interdependent. The mycelium does not think, but it facilitates thought, or something like it. The signal travels. The plants respond. The network functions, silent and efficient, beneath the soil. Fungal spores are microscopic, often measuring just a few micrometers across, and they are produced in staggering numbers. A single giant puffball can release 7 trillion spores, each one capable of growing into a new fungus if it lands in the right conditions. Spores are dispersed by wind, water, animals, and insects, and they can remain viable for years, waiting for the perfect moment to germinate. Spores are invisible to the naked eye, but when released in large numbers, they form clouds, brown, white, or yellow, that drift on the slightest breeze. They have no smell, no taste, only potential. Some spores are smooth, some are spiny, some are shaped like stars or spirals, each one a tiny work of geometric art. Spores teach us that abundance is a strategy, that survival often depends on sheer numbers, that most attempts will fail but a few will succeed. and that is enough. The spores do not know where they will land. They simply drift, carried by forces beyond their control, waiting for the chance to grow. The spores release, the wind carries them. The future scatters, invisible and patient, across the land. Mycorrhizae are partnerships between fungi and plant roots, and they are essential to most terrestrial ecosystems. The fungus colonizes the root, extending its hyphae far into the soil, increasing the plant's access to water and nutrients, especially phosphorus and nitrogen. In return, the plant provides the fungus with sugars produced through photosynthesis. More than 90% of plant species form mycorrhizal associations. The roots and hyphae are intertwined, almost indistinguishable, and the soil around them is rich and dark, teeming with microbial life. The partnership is invisible from above, but its effects are everywhere. Healthier plants, more robust growth, greater resilience to drought and disease. The forest depends on this collaboration. Mycorrhizae teach us that mutualism is not rare but fundamental, that most organisms survive not through competition, but through cooperation, that the boundaries between self and other are often blurred. The fungus and the plant are separate organisms, but they function as one, each incomplete without the other. The hyphae extend, the nutrients flow, the partnership thrives, ancient and essential, beneath the surface. Some fungi are bioluminescent, producing a cold, green glow through chemical reactions in their mycelium or fruiting bodies. The light is faint, visible only in complete darkness, and it serves purposes we do not fully understand, perhaps to attract insects that will disperse spores, perhaps as a byproduct of metabolic processes. The glowing fungi are found in forests around the world, turning fallen logs and forest floors into scenes from a fairy tale. The light is soft and eerie, green or blue-green, and it does not flicker. It simply glows, constant and cool, illuminating nothing but itself. The fungi smell of earth and decay, and the wood they grow on is soft and crumbling, riddled with mycelial threads. The forest at night is silent, and the glow is the only light, a reminder that life exists even in darkness. Bioluminescent fungi teach us that light does not always come from the sun, that beauty exists in the darkest places, that the forest is alive in ways we rarely see. The fungi glow not for us, but for themselves, or for the insects they attract, indifferent to our wonder. The chemicals react, the light glows, the forest shimmers, soft and green, in the dark. Fungi can break down almost anything. Some species digest lignin, the tough polymer that gives wood its strength, allowing them to decompose trees. Others break down cellulose, chitin, keratin, even synthetic materials like plastics and petroleum products. Scientists are researching fungi as tools for bioremediation, using them to clean up oil spills, toxic waste, and polluted soil. The fungi grow on whatever they consume, their mycelium spreading through contaminated soil or oil-soaked ground. The process is slow but relentless, and the fungi do not tire. They simply grow, secreting enzymes, absorbing nutrients, transforming poison into harmless byproducts. The smell of decomposition is strong, earthy, sometimes acrid, sometimes sweet, and the substrate gradually crumbles, losing structure as the fungi digest it. Fungi teach us that waste is a human concept, that nature recycles everything, that even the most toxic substances can be broken down given enough time and the right organism. The fungi do not judge, they simply consume, transforming the unusable into the usable. The enzymes work. The toxins break down, the soil heals, slowly and patiently, through fungal alchemy. Fairy rings are circular patterns of mushrooms that appear in forests and grasslands, formed when mycelium grows outward from a central point in all directions. The oldest fairy rings are centuries old, expanding a few inches each year, and some are more than half a mile in diameter. The grass inside the ring is often darker and more lush, fertilized by the nutrients the fungus releases as it decomposes organic matter. The mushrooms appear overnight, forming a perfect circle, and they disappear just as quickly, leaving only the ring of darker grass. The air smells of earth and mushrooms, and the grass inside the ring feels softer, thicker, fed by the hidden work of the mycelium below. Folklore attributed the rings to dancing fairies or witches, but the truth is stranger: a single organism growing outward year after year in a perfect geometric pattern. Fairy rings teach us that nature follows rules, that growth is not random but patterned, that the mycelium beneath the soil is organized in ways we are only beginning to understand. The ring expands, patient and precise, a living compass drawn in mushrooms and grass. The mycelium grows, the ring expands, the pattern holds, ancient and mathematical in the grass. Fungi are ancient. They appeared on land more than 400 million years ago, long before flowering plants, and they may have been essential to the colonization of land by plants. Early plants lacked true roots, and they likely relied on mycorrhizal fungi to extract nutrients from the soil. Fossils show fungal hyphae intertwined with the earliest plant tissues, evidence of a partnership that has endured for hundreds of millions of years. The fossils are delicate, preserved in stone, and they show structures that are unmistakably fungal, branching hyphae, spores, fruiting bodies. The stone smells faintly of minerals, and the fossils are often barely visible, requiring magnification to see. But they are there, proof that fungi have been shaping the world since the beginning of terrestrial life. Fungi teach us that the past is present, that the partnerships we see today are echoes of ancient collaborations, that the mycelium beneath our feet is part of a lineage older than trees, older than flowers, older than almost anything alive on land. The fungi remember in their genes, in their structures, in their partnerships. The hyphae fossilize. The stone preserves. The memory holds, ancient and patient, in the rock. Ice is not frozen water. It is water in a different state. A crystalline solid where molecules lock into hexagonal lattices, creating a structure that is less dense than liquid water. This is why ice floats, why lakes freeze from the top down, why aquatic life can survive beneath a layer of ice. If ice sank, every body of water would freeze solid from the bottom up, and life as we know it would not exist. Ice is an accident of chemistry that makes the world habitable. Ice is cold and hard, smooth or textured, depending on how it formed. It squeaks when you walk on it, cracks when it shifts, and it smells of nothing, pure and clean, like the absence of scent. When you touch it, it burns with cold, and if you hold it long enough, it begins to melt, the surface becoming slick and wet. Light passes through clear ice, refracting into blues and whites, and air bubbles trapped inside create patterns like frozen stars. Ice teaches us that structure matters, that the arrangement of molecules determines properties, that what seems solid is simply molecules moving slowly. Ice is temporary, always melting or sublimating, always returning to water or vapor, but while it exists, it shapes the world. The molecules slow, the lattice forms, the ice holds cold and patient until the temperature rises. Glaciers are rivers of ice, flowing downhill under their own weight at speeds measured in inches per year. They form in places where more snow falls in winter than melts in summer, and over centuries, the accumulated snow compresses into dense blue ice. Glaciers cover about 10% of Earth's land surface, and they contain roughly 70% of the planet's fresh water. During the last ice age, glaciers covered nearly a third of the land, Glacial ice is blue because it is so dense that it absorbs all colours of light except blue, which it reflects. The surface is rough and crevassed, scarred by the slow movement of the ice, and the air near a glacier is cold and damp, smelling faintly of minerals and ancient snow. When a glacier caps, when chunks of ice break off and fall into the water, the sound is like thunder, echoing across the landscape. Glaciers teach us that even the slowest forces can reshape continents, that patience is power, that ice can carve valleys and move mountains given enough time. The glacier does not hurry. It flows grinding rock to powder, carrying boulders hundreds of miles, indifferent to the passage of centuries. The snow accumulates, the ice compresses. The glacier flows, slow and relentless, down the mountain. Ice cores are cylinders of ice drilled from glaciers and ice sheets, and they contain a record of Earth's climate stretching back hundreds of thousands of years. Layers of snow accumulate year after year, trapping air bubbles, dust, pollen, and volcanic ash. By analysing the chemistry of the ice and the composition of the trapped air, scientists can reconstruct past temperatures, atmospheric CO2 levels, and even the occurrence of major volcanic eruptions. The ice is dense and cold, and when you hold a piece of it up to the light, you can see the layers, thin bands of varying clarity, each one representing a year of snowfall. The air bubbles are tiny, barely visible, but they contain the atmosphere of the past, preserved in frozen time. The ice smells of nothing, pure and ancient, and it is so cold that it stings your fingers. Ice cores teach us that the past is not lost, that the Earth keeps records, that climate is not static but constantly changing. The ice remembers, holding the memory of ancient atmospheres, ancient climates, ancient worlds, waiting to be read. The snow falls, the layers compress. The ice preserves, holding the past in frozen silence. Permafrost is soil that remains frozen for at least 2 consecutive years, and it covers roughly a quarter of the northern hemisphere's land surface. Some permafrost has been frozen for tens of thousands of years, and it contains the preserved remains of plants, animals, and microorganisms from the last ice age. As the climate warms, permafrost is thawing, releasing carbon dioxide and methane, greenhouse gases that accelerate warming in a dangerous feedback loop. Permafrost is hard as concrete when frozen, and it smells of earth and decay when it thaws. The ground is uneven, pocked with depressions where the ice has melted and the soil has collapsed. In some places, you can see the remains of ancient animals, mammoth tusks, bison bones, preserved in the frozen ground for millennia. The air is cold and still, and the landscape is barren, dotted with stunted trees and low shrubs. Permafrost teaches us that the past is not always past, that what was frozen can thaw, that the Earth's systems are interconnected in ways we are only beginning to understand. The permafrost holds the carbon of ancient forests, ancient grasslands, and as it melts, that carbon returns to the atmosphere, warming the world. The ground freezes, the carbon locks away, the permafrost holds, until the temperature rises. Icebergs are chunks of glacial ice that have broken off and floated into the ocean. Only about 10% of an iceberg is visible above the water. The rest is hidden below the surface, a massive underwater structure that can extend hundreds of feet down. Icebergs are made of fresh water, not salt water, and they can drift for years, slowly melting as they move through warmer waters. Icebergs are white or blue, sculpted by wind and waves into fantastical shapes. Arches, spires, smooth curves. The surface is rough and pitted, and the ice is so dense that it rings when struck. The water around an iceberg is cold and clear, and the air smells of salt and ice. When an iceberg melts, it releases ancient air trapped in the ice, air that was last breathed thousands of years ago. Icebergs teach us that what we see is often only a fraction of what exists, that the hidden is often larger and more significant than the visible, that the ocean is full of unseen structures. The iceberg drifts, silent and massive, slowly dissolving into the sea. The ice breaks, the berg floats, the ocean claims it, slowly and patiently, over years. Snowflakes are ice crystals that form in clouds when water vapor freezes around a tiny particle of dust or pollen. As the crystal falls through the cloud, it encounters different temperatures and humidity levels, which cause it to grow in unique ways. The result is that no two snowflakes are exactly alike. Each one is a unique geometric structure, a six-sided fractal shaped by the conditions it encountered on its journey to the ground. Snowflakes are delicate and intricate, with branches and patterns that seem impossibly precise. They are white or translucent, and they melt almost instantly when they touch your skin. The air during a snowfall is quiet and still, muffled by the falling snow, and the world becomes soft and white, blanketed in silence. Snow smells clean and cold, like frozen water and the absence of scent. Snowflakes teach us that beauty emerges from chaos, that randomness can create order, that the same basic rules, hexagonal symmetry, molecular bonding, can produce infinite variation. The snowflake does not know it is unique. It simply falls, a tiny crystal in a storm of billions. The vapor freezes, the crystal grows, the snowflake falls, unique and ephemeral, to the ground. The Antarctic ice sheet is the largest single mass of ice on Earth, covering an area larger than the United States and Mexico combined. It contains about 90% of the world's ice and 70% of its fresh water. If it melted completely, global sea levels would rise by nearly 200 feet, drowning every coastal city on the planet. The ice is up to 3 miles thick in places, and it has been accumulating for millions of years. The ice sheet is vast and white, stretching to the horizon in every direction. The surface is wind-scoured and rippled, and the air is so cold and dry that it feels like breathing glass. The silence is absolute. No birds, no insects, no running water, only the occasional crack of shifting ice or the moan of the wind. The ice smells of nothing, pure and ancient, and the light is blinding, reflecting off the white surface. The Antarctic ice sheet teaches us that stability is relative, that what seems permanent can change, that the ice that has existed for millions of years is now melting at the edges, retreating in the face of a warming climate. The ice sheet does not care. It simply exists, massive and patient, holding the memory of ancient climates. The snow accumulates, the ice thickens, the sheet holds, cold and vast, at the bottom of the world. Glacial erratics are boulders that have been transported by glaciers and deposited far from their source, sometimes hundreds of miles away. They are often made of rock types that do not occur naturally in the area where they are found, and they can be enormous. Some weigh thousands of tons. Erratics are evidence of past ice ages, proof that glaciers once covered landscapes that are now temperate. The boulders are weathered and lichen-covered, sitting incongruously in fields or forests where the bedrock is entirely different. They are cold and rough, and they smell of stone and moss. The landscape around them is often flat or gently rolling, shaped by the passage of glaciers, and the erratics stand as silent witnesses to a time when ice ruled the land. Glacial erratics teach us that the past leaves traces, that the landscape is a palimpsest, written and rewritten by ice and water and wind, that the boulders we see today were carried by forces we can barely imagine. The erratics do not move. They simply sit patient and immovable, waiting to tell their story. The glacier carries. The ice melts. The boulder remains, a memory of ice in a world of green. Ice ages are periods when global temperatures drop, and ice sheets expand to cover large portions of the continents. Earth has experienced at least 5 major ice ages over the past 2.5 billion years, each lasting millions of years and punctuated by warmer interglacial periods. We are currently in an interglacial period called the Holocene, which began about 11,700 years ago. The next ice age, if natural cycles continue, may begin in tens of thousands of years. The evidence of past ice ages is everywhere. Glacial valleys, moraines, erratics, striations carved into bedrock by moving ice. The landscape has been shaped and reshaped by ice, and the climate we experience today is a brief warm spell in a much longer cycle. The air is temperate now, but the ice remembers, locked in glaciers and ice sheets, waiting for the climate to shift again. Ice ages teach us that change is the only constant, that the climate we think of as normal is an anomaly, that the Earth has been much colder and much warmer than it is now. The ice ages do not care about human timescales. They operate on geological time, patient and inevitable. The temperature drops. The ice advances, the cycle turns, slow and patient over millennia. Cryoconite holes are small, water-filled depressions on the surface of glaciers, formed when dark particles, dust, soot, algae, absorb sunlight and melt the ice beneath them. The particles sink into the ice, creating cylindrical holes that can be several feet deep. These holes are ecosystems unto themselves, home to bacteria, algae, and tiny invertebrates that have adapted to life in one of the harshest environments on Earth. The holes are dark against the white ice, filled with murky water that smells faintly organic. The ice around them is smooth and wet, and the water is cold enough to numb your fingers in seconds. The organisms living in the holes are invisible to the naked eye, but they are there, thriving in the meltwater, feeding on sunlight and minerals. Cryoconite holes teach us that life finds a way, that even on a glacier, in water just above freezing, ecosystems can exist, that the boundaries of habitability are wider than we imagine. The holes are temporary, freezing over in winter, or draining away as the glacier melts. But while they exist, they are worlds. The particles absorb, the ice melts, the hole forms, a tiny oasis on the frozen surface. Glacial lakes form when glaciers retreat, leaving behind depressions that fill with meltwater. These lakes are often a brilliant turquoise or milky white, coloured by fine particles of rock flour, sediment ground to powder by the glacier and suspended in the water. Glacial lakes are cold and clear, and they are often surrounded by barren, rocky landscapes that are still recovering from the retreat of the ice. The water is so cold that it numbs your skin instantly, and it smells clean and mineral, like melted snow. The colour is striking, bright blue or green depending on the concentration of rock flour, and the surface is often calm, reflecting the mountains and sky. The air is cool and damp, and the only sounds are the drip of meltwater and the occasional crack of distant ice. Glacial lakes teach us that retreat is not always loss, that the melting of glaciers creates new landscapes, new ecosystems, new opportunities for life. The lakes are young, geologically speaking, and they are changing rapidly as the glaciers continue to shrink. The glacier retreats, the depression fills. The lake forms cold and brilliant in the valley. Deep time is the concept that Earth's history spans billions of years, a timescale so vast that human history is barely a footnote. The ice we see today is the product of processes that have been operating for millions of years, and the glaciers that carved the landscape did so over tens of thousands of years. To understand ice, to understand glaciers, is to understand deep time. To grasp that the world we see is not permanent, but constantly changing, shaped by forces that operate on timescales we cannot directly perceive. The evidence of deep time is everywhere, in the layers of ice cores, in the striations on bedrock, in the fossils preserved in permafrost. The landscape is a record, written in stone and ice, of processes that began long before we existed and will continue long after we are gone. The air is still and the ice is silent, but both are part of a story that spans eons. Deep time teaches us humility, that our lives are brief, that the earth is ancient and patient, that the ice has seen the rise and fall of species, the drift of continents, the cycling of climates. The ice does not hurry, it simply exists, a frozen record of the past, waiting for the future. The eons pass, the ice records. The story continues, patient and eternal, in frozen time. Deserts are not defined by heat but by dryness. A desert is any region that receives less than 10 inches of precipitation per year, and by that measure, Antarctica is the largest desert on Earth. The Sahara, the Gobi, the Mojave. These are hot deserts, but they share with Antarctica the same fundamental characteristic. Water is scarce, and life must adapt or perish. The desert does not apologize for its harshness. It simply exists, vast and indifferent, shaped by wind and time. Sand is not uniform. Each grain is a fragment of rock worn smooth by wind and water over thousands or millions of years. The grains are quartz, feldspar, gypsum, or volcanic glass, and they range in colour from white to red to black. When you run sand through your fingers, it feels dry and slightly rough, and it smells faintly of minerals and sun-baked stone. The wind moves the sand in waves, creating dunes that shift and migrate, reshaping the landscape year by year. The desert teaches us that scarcity breeds resilience, that life does not require abundance, that beauty exists in barrenness. The sand does not hold water, does not nourish plants, and yet the desert is alive, filled with creatures and plants that have learned to survive on almost nothing. The wind blows, the sand shifts. The desert breathes dry and patient. Under the relentless sun, sand dunes sing. In certain deserts around the world, the Sahara, the Gobi, the deserts of California and Nevada, large dunes produce a low rumbling sound when the sand slides down their slopes. The sound can be as loud as a low-flying airplane, and it can last for several minutes. Scientists believe the sound is caused by the friction between sand grains, which vibrate at specific frequencies depending on the size and shape of the grains. The sound is eerie and otherworldly, a deep hum or roar that seems to come from the dune itself. The sand is warm and dry, and it flows like water when disturbed, cascading down the slope in rivers of golden grains. The air is still and hot, and the only other sound is the whisper of wind across the surface of the dune. Singing dunes teach us that the earth has voices we rarely hear, but the landscape is not silent, but filled with sounds beyond the range of our everyday experience. The dunes do not sing for us. They sing because of physics, because of the precise arrangement of grains and the angle of the slope, indifferent to our wonder. The sand slides, the grains vibrate. The dune sings, low and resonant, in the desert silence. The Atacama Desert in Chile is the driest place on Earth. Some weather stations in the Atacama have never recorded rainfall. The desert is so dry that mummified remains of animals and humans can be found perfectly preserved, their tissues intact after centuries. The soil is sterile, almost devoid of bacteria, and NASA uses the Atacama as a testing ground for Mars rovers because the conditions are so similar to the Martian surface. The landscape is barren and rocky, with vast salt flats and dry lake beds that crack in geometric patterns. The air is thin and dry, and it smells of dust and minerals. The silence is absolute. No birds, no insects, no rustling leaves. Only the occasional whisper of wind. The sky is so clear that the Atacama is home to some of the world's most powerful telescopes. their lenses pointed at stars undimmed by moisture or pollution. The Atacama teaches us that extremes exist, that there are places on Earth where rain is not a given, where life clings to the margins, where the landscape resembles another planet. The desert does not change. It simply waits, dry and patient, for the rare rain that may come once in a decade. The sky is clear. The ground is dry. The desert waits, silent and sterile, under the stars. Desert plants have evolved extraordinary adaptations to survive with minimal water. The saguaro cactus can store hundreds of gallons of water in its thick pleated stem, expanding like an accordion when it rains, and slowly contracting as it uses the water. The creosote bush spaces itself evenly across the desert floor, each plant releasing chemicals into the soil that prevent other creosote seeds from germinating nearby, ensuring that each plant has access to enough water. Some desert plants have roots that extend 100 feet down, tapping into underground aquifers. The saguaro is tall and columnar, its surface ribbed and covered in spines that provide shade and protect against herbivores. The creosote smells sharp and resinous, especially after rain, a scent that is the signature of the desert. The plants are spaced far apart, and the ground between them is bare, rocky, and hot. The air shimmers with heat, and the only movement is the slow sway of a cactus arm in the wind. Desert plants teach us that survival requires innovation, that scarcity forces adaptation, that life finds solutions we would never imagine. The plants do not compete directly. They space themselves, conserve water, and wait for the rare rains that will allow them to bloom. The roots extend, the water stores, the plants endure, patient and resilient, in the heat. Oases are places in the desert where water reaches the surface, creating pockets of lush vegetation surrounded by barrenness. They form where underground aquifers intersect with the surface, or where rivers flow down from distant mountains. Oases have been vital to human survival in deserts for millennia, serving as waypoints for trade routes and centers of settlement. The contrast between the green of the oasis and the brown of the surrounding desert is stark and surreal. The water in an oasis is cool and clear, and it smells faintly of minerals and vegetation. Palm trees grow tall and dense, their fronds rustling in the breeze, and the ground is soft and damp, covered in grass and reeds. The air is cooler here, humid compared to the dry desert, and the sound of water, trickling, dripping, flowing, is constant and soothing. Oases teach us that life clusters around resources, that water is the currency of survival, but even in the harshest environments, there are refuges. The oasis does not spread, it remains contained, a small island of green in a sea of sand, sustained by the hidden water below. The water surfaces, the plants grow, the oasis thrives, a green jewel in the desert's heart. Sandstorms, also called haboobs, are massive walls of dust and sand driven by strong winds, often associated with thunderstorms. They can be thousands of feet high and stretch for miles, turning day into night as they engulf the landscape. The sand and dust reduce visibility to near zero, and the wind can reach speeds of 60 miles per hour or more. Sandstorms are common in the Sahara, the Arabian Desert, and the deserts of the American Southwest. The wall of sand approaches like a solid thing, brown or red or orange, blotting out the sun. The air becomes thick and gritty, and the sand stings exposed skin like tiny needles. The wind roars, and the world disappears into a choking, swirling chaos. The smell is of dust and earth, dry and acrid, and the taste is gritty, coating your teeth and tongue. Sandstorms teach us that the desert is not static, that the wind can reshape the landscape in hours, that what seems solid, the dunes, the sand, is constantly in motion. The storm does not discriminate. It buries roads, buildings, anything in its path, and then it passes, leaving the desert transformed. The wind rises, the sand lifts, the storm engulfs chaotic and blinding the desert. Desert nights are cold. Without the insulating effect of moisture in the air, the heat absorbed during the day radiates back into space as soon as the sun sets. Temperatures can drop by 50 degrees Fahrenheit or more between day and night, and in some deserts, frost forms on the ground even though the daytime temperature exceeded 100 degrees. The desert is a place of extremes, swinging between scorching heat and bitter cold within hours. The night sky in the desert is spectacular, filled with stars so numerous that the Milky Way casts shadows. The air is cold and still, and the sand, which was too hot to touch during the day, is now cool and damp with dew. The silence is profound, broken only by the occasional call of a nightjar or the rustle of a nocturnal rodent. The desert smells different at night, cooler, cleaner, with a faint hint of moisture. Desert nights teach us that balance is not constant, that the same place can be two different worlds depending on the time of day, that extremes define the desert as much as scarcity. The desert does not moderate. It swings between heat and cold, light and dark, with no middle ground. The sun sets, the heat escapes. The desert cools, silent and star-filled, in the night. The Namib Desert is home to some of the tallest sand dunes in the world, some reaching heights of over 1,000 feet. The dunes are ancient, some more than 5 million years old, and they are constantly shifting, sculpted by winds that blow from different directions throughout the year. The sand is red or orange, coloured by iron oxide, and the dunes create a landscape of sweeping curves and sharp ridges that seem almost sculptural. The sand is fine and soft, and it flows easily, making climbing the dunes exhausting. Each step sinks deep, and progress is slow. The surface is hot during the day, too hot to touch, and the air shimmers with heat. The wind is constant, carrying sand that hisses as it moves across the dunes. The smell is of dry earth and minerals, and the silence is broken only by the wind and the occasional rumble of sliding sand. The Namib dunes teach us that age does not mean permanence, that even structures millions of years old are constantly changing, that the desert is a sculptor, shaping and reshaping the landscape with infinite patience. The dunes do not resist the wind. They flow with it, adapting, shifting, enduring. The wind shapes. The sand flows. The dunes rise, ancient and ever-changing, in the desert. Desert animals have adapted to survive with little or no water. The kangaroo rat can live its entire life without drinking, obtaining all the moisture it needs from the seeds it eats. The camel can go weeks without water, storing fat in its hump that can be metabolized into water and energy. The fennec fox has enormous ears that radiate heat, keeping it cool in the scorching desert sun. These adaptations are not luxuries but necessities, the result of millions of years of evolution in one of the harshest environments on Earth. The animals are mostly nocturnal, avoiding the heat of the day by sheltering in burrows or under rocks. The kangaroo rat is small and quick, its fur soft and pale, and it moves in sudden bursts, disappearing into the sand. The camel is large and patient, its eyes half closed against the sun, its footsteps slow and deliberate. The fennec fox is delicate and alert, its ears swiveling to catch the faintest sound. Desert animals teach us that adaptation is survival, that life does not require ideal conditions, that the harshest environments produce the most specialized creatures. The animals do not complain. They simply live perfectly suited to a world that would kill most other organisms. The animals adapt, the strategies evolve, the desert sustains, harsh and unforgiving. The adapted. Mirages are optical illusions caused by the refraction of light through layers of air at different temperatures. In the desert, the ground heats the air directly above it, creating a layer of hot air beneath cooler air. Light traveling through these layers bends, creating the illusion of water on the horizon, a shimmering reflective surface that disappears as you approach. Mirages are not hallucinations but real optical phenomena, visible to cameras as well as human eyes. The mirage shimmers and dances, always just out of reach, and it looks exactly like water, a lake or a puddle reflecting the sky. The air is hot and dry, and the ground radiates heat in waves that distort the landscape. The mirage is silent, intangible, a trick of physics that has lured thirsty travelers for millennia. Mirages teach us that perception is not always reality, that the desert deceives, that what we see is shaped by the conditions through which light travels. The mirage does not lie. It simply shows us what the physics of light and heat create, indifferent to our thirst. The light bends, the air shimmers, the mirage appears, false and beautiful, on the horizon. Desert pavement, also called desert varnish, is a surface layer of tightly packed stones that forms in some deserts when wind removes the finer particles of sand and dust, leaving only the larger rocks behind. Over time, the rocks become coated with a dark layer of manganese and iron oxides, giving them a polished, varnished appearance. The pavement can be thousands of years old, and it is remarkably stable, protecting the soil beneath from further erosion. The stones are smooth and dark, and they click softly when you walk on them. The surface is hard and flat, almost like a cobblestone street, and it stretches for miles, broken only by occasional patches of sand or scrub. The air is dry and hot, and the stones radiate heat, making the surface shimmer. The varnish has no smell, only the faint mineral scent of sun-baked rock. Desert pavement teaches us that protection comes from exposure, that the wind that strips away the soil also creates a surface that resists further erosion, that the desert builds its own armor. The pavement does not grow. It simply persists, a stable surface in a landscape of constant change. The wind strips. The stones remain. The pavement forms dark and stable on the desert floor. Rain in the desert is a transformation. When it finally comes, after months or years of drought, the desert explodes into life. Seeds that have lain dormant in the soil for decades germinate within days, and the desert floor becomes a carpet of wildflowers, yellow, purple, red, orange. The bloom lasts only a few weeks, just long enough for the plants to flower, produce seeds and die, leaving the next generation of seeds to wait for the next rain. The air after rain smells of wet earth and creosote, sharp and clean, and the ground is damp and soft. The flowers are delicate and bright, their petals thin as tissue paper, and they sway in the breeze. Insects appear from nowhere. Bees, butterflies, beetles, drawn by the sudden abundance. The desert, which seemed lifeless days before, is now vibrant and alive. Desert rain teaches us that dormancy is not death, that patience is rewarded, that life waits for the right moment and then seizes it with astonishing speed. The desert does not bloom for us. It blooms because the rain has come, because the seeds have waited, because the cycle continues, the rain falls. The seeds wake, the desert blooms, brief and brilliant, in the sun. An ecosystem is not a collection of organisms, but a web of relationships, each species connected to dozens or hundreds of others through feeding, competition, symbiosis, and predation. Remove one species, and the effects ripple outward in ways that are often unpredictable. Add a species, and the web reconfigures, sometimes catastrophically. The balance is not static but dynamic, constantly adjusting, constantly shifting, maintained not by design but by the accumulated interactions of millions of organisms over millions of years. An ecosystem smells of its dominant elements: salt and seaweed in a tidal pool, pine and soil in a forest, grass and manure in a savanna. The sounds are layered: bird calls, insect hums, the rustle of leaves or grass, the distant calls of predators. The air feels different in each ecosystem: humid in a rainforest, dry in a grassland, cool and damp in a temperate forest. Every ecosystem has a texture, a rhythm, a character shaped by the organisms that inhabit it. Ecosystems teach us that nothing exists in isolation, that every action has consequences, that the web of life is more fragile and more resilient than we imagine. The ecosystem does not strive for balance. It simply exists, and balance emerges from the chaos of countless interactions. The relationships intertwine. The web holds. The ecosystem breathes, complex and patient, through time. Predators regulate prey populations, preventing overgrazing and overbrowsing that would destroy vegetation. When wolves were reintroduced to Yellowstone National Park in 1995, after being absent for 70 years, the effects cascaded through the ecosystem. Elk populations declined and changed their behavior, avoiding open valleys where they were vulnerable. This allowed willows and aspens to recover, which stabilized riverbanks and provided habitat for beavers. The beavers built dams, creating wetlands that supported fish, amphibians, and birds. The wolves did not intend to restore the ecosystem. They simply hunted, and the ecosystem responded. The wolves moved through the snow, their breath visible in the cold air, and their howls echo across the valleys. The elk are wary, clustering in groups, their eyes scanning the tree line. The willows grow tall along the rivers, their branches thick and green, and the beavers work in the twilight, gnawing through trunks and dragging branches to their dams. The air smells of pine and wet earth, and the sound of running water is constant. Predators teach us that control is not domination, that the presence of a hunter creates space for others, that fear is a force that shapes landscapes. The wolves do not manage the ecosystem. They are part of it, and their presence allows the web to function. The predators hunt, the prey adapt. The ecosystem shifts, finding a new balance. Pollinators, bees, butterflies, birds, bats, are essential to the reproduction of more than 75% of flowering plants, including many of the crops humans depend on for food. Without pollinators, ecosystems would collapse, and human agriculture would fail. A single honeybee colony can pollinate millions of flowers in a season, and the value of pollination services worldwide is estimated in the hundreds of billions of dollars. The pollinators do not work for us. They work for themselves, seeking nectar and pollen, and the plants benefit from their visits. The bees move from flower to flower, their legs dusted with yellow pollen, and the air hums with their activity. The flowers are bright and fragrant, their petals open to the sun, and the scent is sweet and complex. Roses, lavender, clover, wildflowers. The butterflies are delicate and colourful, their wings catching the light. And the hummingbirds hover, their wings a blur, their beaks probing deep into tubular flowers. Pollinators teach us that mutualism sustains the world, that the smallest creatures perform the most essential tasks, that the beauty of flowers is not decoration but function. The pollinators do not know they are essential. They simply feed, and in feeding, they sustain the web of life. The wings beat, the pollen transfers, the flowers reproduce, sustained by the smallest workers. Decomposers, bacteria, fungi, insects, worms, break down dead organic matter, recycling nutrients back into the soil where they can be used by plants. Without decomposers, dead material would accumulate, nutrients would be locked away, and ecosystems would grind to a halt. A single earthworm can process its own weight in soil every day, aerating the ground and mixing organic matter with minerals. The decomposers are invisible or overlooked, but they are the foundation of the nutrient cycle. The forest floor is soft and damp, covered in fallen leaves that crumble at the touch. The smell is rich and earthy, like compost and mushrooms, and the soil is dark and crumbly, teeming with life. Beetles scurry through the leaf litter, millipedes curl into spirals when disturbed, and the earthworms tunnel through the soil, leaving behind castings that enrich the earth. The decomposers are silent, working in darkness, transforming death into life. Decomposers teach us that endings are beginnings, that death feeds life, that the cycle is closed by the smallest and least celebrated organisms. The decomposers do not rest. They work constantly, breaking down, recycling, sustaining the web. The matter decays, the nutrients release. The cycle turns, sustained by the unseen workers. Keystone species are organisms that have a disproportionately large effect on their ecosystem relative to their abundance. The sea otter is a keystone species in kelp forests. Otters eat sea urchins, which eat kelp. Without otters, urchin populations explode and they devour the kelp, turning vibrant underwater forests into barren urchin barrens. With otters, the kelp thrives, providing habitat for fish, invertebrates, and marine mammals. The otter does not manage the ecosystem. Its presence simply allows the ecosystem to function. The otters float on their backs, cracking open urchins on rocks balanced on their chests, and their fur is thick and sleek, shedding water in droplets. The kelp sways in the current, tall and green, and the water is cool and clear, filled with fish darting through the fronds. The urchins are spiny and purple, clustered on the rocks, and the sound is the crash of waves and the distant bark of sea lions. Keystone species teach us that importance is not measured by size or numbers, that a single species can hold an ecosystem together, that the web is held by threads we often do not see. The otter does not know it is essential. It simply eats, and the ecosystem responds. The otter hunts, the urchins decline, the kelp recovers, and the ecosystem holds. Succession is the process by which ecosystems change over time, recovering from disturbances or developing on new land. After a forest fire, the first plants to colonize the burned ground are often grasses and wildflowers, which stabilize the soil and add nutrients. Shrubs follow, then fast-growing trees like aspens and pines, and eventually, slower-growing trees like oaks and maples take over, creating a mature forest. The process can take decades or centuries, and each stage creates conditions that allow the next stage to develop. The burned forest smells of charcoal and ash, and the ground is black and bare, dotted with the charred stumps of trees. Within weeks, green shoots appear, grasses, fireweed, lupines, and the air smells of new growth and rain. The shrubs grow thick, and the young trees rise among them, their leaves bright and green. The forest is rebuilding, slowly and patiently, following a script written by millions of years of evolution. Succession teaches us that ecosystems are resilient, that disturbance is not destruction, that nature does not need our help to recover, only time and space. The forest does not mourn what was lost. It simply grows, stage by stage, toward a new equilibrium. The fire clears. The plants colonize, the forest returns, patient and inevitable. Nutrient cycles, carbon, nitrogen, phosphorus, water, are the pathways through which essential elements move through ecosystems. Carbon cycles from the atmosphere into plants through photosynthesis, into animals through feeding, into the soil through decomposition, and back into the atmosphere through respiration and combustion. Nitrogen is fixed from the atmosphere by bacteria, absorbed by plants, consumed by animals, and returned to the soil through waste and decay. These cycles are ancient, operating for billions of years, and they are essential to all life. The cycles are invisible, but their effects are everywhere. The air you breathe contains carbon that was once part of a tree, an animal, a microbe. The nitrogen in your DNA was once in the atmosphere, fixed by bacteria in the soil, absorbed by a plant, eaten by an animal. The water in your cells has cycled through oceans, clouds, rivers, and organisms countless times. The cycles connect everything, linking the living and the non-living in a web that spans the planet. Nutrient cycles teach us that matter is conserved, that the atoms in our bodies are ancient, that we are made of recycled stardust and ocean water and ancient air. The cycles do not pause, they turn, constantly and patiently, sustaining life. The elements cycle, the pathways connect, the web holds, ancient and essential. Biodiversity is the variety of life in an ecosystem, and it is a measure of resilience. Ecosystems with high biodiversity are more stable, more productive, and more resistant to disturbances than ecosystems with low biodiversity. A diverse ecosystem has redundancy. If one species declines, others can fill its role. A monoculture, by contrast, is fragile, vulnerable to disease, pests, and environmental changes. Biodiversity is not a luxury, but a necessity, the foundation of ecosystem health. A diverse ecosystem is a sensory overload. Dozens of bird species calling, hundreds of plant species blooming, thousands of insect species buzzing and crawling. The smells are layered, flowers, soil, water, decay, and the textures are varied. Rough bark, smooth leaves, soft moss, hard stone. The diversity is not chaos but complexity, each species occupying a niche, each one contributing to the whole. Biodiversity teaches us that variety is strength, that monocultures are human inventions, that nature thrives on complexity. The ecosystem does not simplify, it diversifies, creating niches and filling them, building resilience through abundance. The species multiply, the niches fill. The ecosystem thrives, complex and resilient. Invasive species are organisms introduced to ecosystems where they did not evolve, and they often lack the predators, parasites, and competitors that keep them in check in their native habitats. The result can be catastrophic. Kudzu smothers forests in the southeastern United States. Zebra mussels clog waterways in the Great Lakes. Cane toads poison predators in Australia. Invasive species disrupt the balance, outcompeting native species and reshaping ecosystems in ways that are often irreversible. The kudzu grows over everything: trees, buildings, power lines, its leaves thick and green, its vines relentless. The forest beneath is dark and suffocated, and the smell is of damp vegetation and decay. The zebra mussels coat every surface, sharp and densely packed, and the water is clearer than it should be, stripped of plankton. The cane toads are large and warty, and they sit in the grass at night, their eyes reflecting the light, their skin toxic to anything that tries to eat them. Invasive species teach us that ecosystems are not infinitely adaptable, that the balance can be broken, that the introduction of a single species can unravel millions of years of evolution. The invasives do not intend harm, they simply thrive, and the ecosystem suffers. The species invades. The balance breaks, the ecosystem struggles, reshaped by the newcomer. Symbiosis is a close, long-term relationship between two species, and it takes many forms. Mutualism benefits both species, like the relationship between flowering plants and their pollinators. Commensalism benefits one species without harming the other, like barnacles on a whale. Parasitism benefits one species at the expense of the other, like ticks on a deer. Symbiotic relationships are everywhere, and they are essential to the functioning of ecosystems. The relationships are often invisible. The bacteria in your gut digest food you cannot digest, and in return, you provide them with a warm, nutrient-rich environment. The fungi in the soil exchange nutrients with plant roots, and both benefit. The cleaner fish remove parasites from larger fish, and both species thrive. The symbioses are ancient, refined over millions of years, and they are woven into the fabric of life. Symbiosis teaches us that cooperation is as important as competition, that survival often depends on partnerships, that the boundaries between organisms are more fluid than we imagine. The symbionts do not negotiate, they simply coexist, and both benefit. Or one benefits, or one suffers. The relationship is the thing. The partners interact, the benefits flow. The symbiosis holds, ancient and essential. Trophic cascades occur when changes at one level of the food web ripple through the entire ecosystem. The classic example is the reintroduction of wolves to Yellowstone. But trophic cascades happen everywhere. When sea otters decline, urchins increase, kelp declines, and fish populations crash. When sharks decline, rays increase, scallops decline, and seagrass beds disappear. The cascades are often counterintuitive, and they reveal how interconnected ecosystems are, how the loss of a single species can reshape an entire landscape. The cascades are invisible until they are not. The forest changes when the wolves return. The kelp forest disappears when the otters vanish. The seagrass beds die when the sharks decline. The changes are slow at first, then accelerating, and by the time they are obvious, the ecosystem has already transformed. The air smells different, the sounds change, the landscape shifts, and the web reconfigures. Trophic cascades teach us that ecosystems are not linear, that cause and effect are not always direct, that the web is more complex than we can fully understand. The cascades do not announce themselves, they simply happen, reshaping the world in ways we often do not predict. The top falls, the cascade begins, the ecosystem transforms, reshaped from above. The Earth is one ecosystem, a single interconnected web of life that spans the planet. The oxygen you breathe was produced by phytoplankton in the ocean and trees in the rainforest. The water you drink has cycled through clouds, rivers, and aquifers, and it has been part of countless organisms. The carbon in your body was once in the atmosphere, absorbed by a plant, eaten by an animal, returned to the soil, and absorbed again. The boundaries we draw between ecosystems, between species, between living and non-living, are human constructs. The Earth does not recognize them. The planet is blue and green and white, swirling with clouds, covered in oceans and forests and ice. The air is thin, a fragile shell of gas that makes life possible, and the soil is alive, teeming with organisms that recycle nutrients and build the foundation for all terrestrial life. The web is vast and complex, and we are part of it, not separate from it, not above it, but woven into it like every other organism. The Earth teaches us humility, that we are not the center, that the web existed long before us and will exist long after, that our survival depends on the health of the whole. The Earth does not need us, we need it. The web connects, the cycles turn. The Earth breathes, patient and ancient, sustaining all life.